Welcome, everyone. Let's get started. First announcement that problem set 5 is out. It is in the Slack, and I'll be adding it to the My Courses page too. Office hours are at their normal times. Are there any questions? It's due the Friday after this Friday at the normal time. Again, end of day Friday. There will be problem set 5 and problem set 6. There'll be one more after this one. Any more questions? Okay, let's get started. So remember that a binary search tree from last time is a binary tree where every node is storing a key, and we require that for every node, the left subtree, so for 6, for example, the left subtree is this, is all the nodes with keys less than or equal to v, and the right subtree is all nodes with keys greater than or equal to v here. And this is not balanced, so the binary search tree could be really skewed. It could be a path, or it could be completely balanced and have logarithmic depth. So we have a lot of algorithms that run in time big O of h, where h is the height of the tree. The maximum height is 1 fewer than the number of keys, and the minimum height is just big O of log n, or actually it's theta of log n. So let's consider a typical binary search tree. There are different ways to define typical, as we'll discuss in the problem set. But suppose that we insert, suppose this is our notion of typical for a binary search tree. Suppose that we insert 1 through n into the tree in random order, starting from nothing. What is the expected height? Well, first of all, actually, what do we think? I'm going to be closer to the minimum height or the maximum height? Some suggestions of the min, or maybe somewhere in between. So let's see what it is. I don't know that there's a clear intuition for this, but yeah, it certainly would be very special to get everything perfectly aligned in a worst case scenario. Oh, and I guess I also wanted to remind everybody, I'm sorry, I forgot to put this in the course announcements, that the whole participating as part of the class thing, it is graded, but there's nothing that you do not have to be saying, you do not have to be participating a certain amount or be having correct answers in the chat. I'm not expecting people to be putting correct answers in the chat. I'm expecting people to be thinking enough to write something that is reflecting you thinking. So there is really no pressure to come up with the right answer. And I'm expecting that most people who come up with the right answers when I ask questions in class are not thinking really fast. Most of them probably have seen something like this before. So if you don't come up with the right answer, that's not a problem. I just basically want to be making sure that everybody is thinking about the problems as we're doing them. Are there any questions about that? And then we'll actually do this proof. I'm terrible at thinking through things like very fast on my feet. So I'm not expecting any of you to do that. Okay. So again, last time we proved the hockey stick identity, which is this beautiful thing in Pascal's triangle where if you take a hockey stick that starts at one of the edges. So if you take this and you go down from 6 choose, you go down from 5 choose 5 to 6 choose 5 to 7 choose 5 to 8 choose 5, you add all of those up, you're going to get 9 choose 5 plus 1. This is the same thing, only it's counted from the other side because Pascal's triangle is symmetric. Symmetric about reflection, or in the middle. Okay, so this is the hockey stick identity. And we also said we were going to use Jensen's inequality. But the form of Jensen's inequality that is expected value of function of x is greater than or equal to function of expected value of x if f is a convex function. And again, that's just another form of Jensen's inequality. It's pretty much the same as the thing we've already seen, the weighted form of Jensen's inequality. Okay. So now let's go back to this problem. What is the expected height of our binary search tree? So let xn be the height of the tree. It's a random variable, depends on n. And then it's, yeah. So we're looking for the expected value of xn. What is the root of the tree? For inserting these things in a random order, how do we work out what the root of the tree is? In terms of the things we're inserting. Some suggestions that it's the first one inserted. Why? Yeah, so there's a suggestion that it is that the root of the tree has the key of the root of the tree is the first thing that has been inserted. So there's, yeah, so responding to different people. Is it the max value? That would be the case in a max heap. We're in a binary search tree, so the property is different. It's not that the max is contained at the top. It's that the max is contained at the right-hand side. Is it the median or the mean? Well, not necessarily. If we insert things in order, for example, if we insert 1, then 2, then 3, then 4, and so on. Remember our insertion process? It was based upon search. So if we insert 1 and then 2, we insert 1 and then 2 comes down on the side of 1, and then 3 comes down here, and then 4 comes down here, and we just make a chain. If we insert n first, then we have n, and then anything smaller than n immediately gets diverted to this side of n. Whatever we put in first will be the root, and there's no way of changing the root. We throw in something, whatever we insert first. I realize this was, I phrased this question maybe badly. Whatever we insert first, the next thing we insert will be compared to it, and it'll go either on the left-hand side or on the right-hand side. We don't know which one, we don't know what we're inserting first, but we know that the root of the tree will stay fixed as we insert new things. Does that make sense? Any questions? Again, we don't know what the first thing is. We're putting them in random order. How can we use this, though? It could generate a highly unbalanced tree. Absolutely. So the root in expectation is the mean. That is correct. What can we do to work out the expected value of xn? Think about maybe what we were doing when we were, say, doing quicksort, and we had a pivot. We were breaking something into everything less than and everything greater than. We can look at the things on the left and right subtrees. In particular, the left-hand subtree is going to contain the numbers 1 through I minus 1. Assuming we've picked I as the root. And the right subtree is going to contain n minus I different numbers. Now, what's the height of the overall tree? It's going to be the max of the height of the individual subtrees plus 1 because we have a root now. So we pushed everything down a bit. I refers to the key, yes. I'm sorry, I should have been a little bit clearer. I'm conflating the node with the key at that node. I apologize. That is technically incorrect for me to do. The root of the tree contains whatever key we insert first. That first key is I. More questions? What are x sub I minus 1 and x sub n minus I? Really good question. So x sub n is the height of the tree, and it's a random variable that depends upon n. I realize I actually didn't quite define these two things, but you're right. I should say formally, like, these are random variables describing the height of the left subtree and the right subtree, respectively. But they are basically exactly the same as x sub n, because x sub I minus 1 is just all the numbers less than I inserted into the left subtree, and all the so how many numbers are in the, I should have spelled this out a little bit more. How many numbers are in the left subtree? The numbers that are in the left subtree are, I'm just going to write this in the chat, are just 1 through I minus 1. And the numbers in the right subtree are going to be the numbers I plus 1 through n. That means that the left subtree has I minus 1 nodes, and the right subtree has n minus I nodes. And so the height of the left subtree is distributed by x I minus 1, which is the same kind of thing as x sub n. It's just the height of a tree with the keys inserted in a random order. Does that make sense? So this is a recursion, basically. We're saying, suppose we insert n things in a random order. We can express that in terms of the random order in which we inserted the numbers 1 through I minus 1. and the random order in which we inserted the numbers I plus 1 through n. The first ones form the left subtree, the last ones form the right subtree. And then the root is whichever one we insert first. More questions, more confusions. I apologize, I should have explained this better. Please let me know if anything is still confusing. Also, if you're ever confused by something, always feel free also just to private message me. You can private message me in the chat. Yeah, so this is a recursion expressing the height of the overall tree in terms of the height of the left subtree, which is everything less than I, and the right subtree, which is everything greater than I. Okay. So now, how do we solve this recursion? It's going to be useful to define another random variable, which is just 2 to the power of x to the n. So let's just rewrite this thing in terms of y. So y sub n is 2 to the x sub n, and likewise y sub I minus 1 is equal to 2 to the x sub I minus 1, and so on. So here we have y sub n, just raising everything to the power 2 here, we get is equal to 2 times, the 1 plus becomes a 2 times max of these things. And then let's do a brutal inequality, which is generally terrible. I would normally never advise you to do this, writing the max of 2 things as less than or equal to the sum of the 2 things. It's definitely true, but it's normally not a very good, not a very tight inequality. And it turns out it'll be fine in this case. Okay. So since each I is equally likely, the thing that we pick first, we can write the expected value of yn as less than or equal to. There's a 1 in n probability of picking I equals 1, a 1 in n probability of picking I equals 2, and all the way up to n. So we can just write it as this mixture of expectations here. Now we do our linearity of expectation. You can pull this 2 out here and just break this up into 2 things. Now what do we do? Can we simplify this even more? We don't have to use the hockey stick identity yet. We'll get there soon. We have this sum of this expectation and sum of this expectation, and rewrite it this. It's a good question. How did we get to y sub n equals 2 times max? Just raising this to the power of 2. If you have 2 to the x equals 1 plus, if you have x equals 1 plus something else, then you raise both sides. You raise 2 to both sides, you get 2 to the x is equal to 2 to the 1 plus, and the 2 to the 1 becomes the 2, and it becomes multiplied by. Good question. Is there any way to simplify this so we don't have to immediately use Jensen's inequality? Notice I got from here to here just by changing like I to I minus 1. It was just a substitution. Somebody suggested symmetry. What would you do with symmetry? What does symmetry mean here? The left and the right subtree are similar. Yeah, they are. So what can you do with this equation? You have a sum of this is expectation of y0 in one of these. It's a sum of expectation of y0, y1, all the way up to yn minus 1. And this is a sum of expectation of yn minus 1, yn minus 2, all the way down to y0. These are the same thing, it's just they're being counted in reverse order. So we can just write this as summing both of these is the same as summing one of them and then multiplying by 2. Questions about anything on this slide? I'm deliberately running you through proofs that have various tricks that you may use in your future proofs. I don't mean specifically like problem set proofs. I mean just in life. So again, what we did was we broke it into, we found a recursion by saying, okay, we wanted to look at the entire tree, which has n nodes. We can break that into the left subtree, which has I minus 1 nodes. We don't know what I is, but we know it has the left subtree has I minus 1 nodes, where I was whatever we inserted first. The right subtree has n minus I nodes. The heights of those trees are the thing that we're looking for only for a smaller number of nodes. And so we can sort of recurse. We can say the overall height is 1 plus the max height of the subtrees. Then we just did a substitution and said instead of height, we're going to consider 2 to the power of height. We did a relaxation, and instead of saying max of 2 things, we said the sum of 2 things. We made that less than or equal to. And then we just rearranged some terms and used linearity of expectation. And now we have that the expected value of y sub n, our random variable, is less than or equal to 4 over n times the sum of the expected value of y sub I. So I goes from 0 to n minus 1. So now we can try to solve this. In particular, we're going to try to prove by induction that the expected value of y sub n is less than or equal to a quarter of n plus 3 choose 3. If we're wondering how we got there, the way that one comes up with these things is typically by starting out the recursion and then seeing what bound comes out. So you would like try y1, you would try y2, y3, and so on, and you just see how good it gets. See if you see a pattern. There's a question. There is an I'm confused. What is confusing? We have not proven this. We are going to try to prove this. Where did it come from? So I'm telling you that this will end up being the solution, but we need to actually prove it. Let's see if we can actually prove it. You could also work out where this came from. It would just be involve sort of trying the first values probably and seeing what pattern comes up. And you would work out that it's probably a cubic polynomial in n. You will also see the intuition of why we chose the substitution of y being 2 to the xn. Yes, this is a let's just guess the solution and then let's prove it. Don't worry, I'm not going to ask you to do something like that on a problem set. This is just a yes. But I mean, this is why sometimes finding the proof is much harder than writing the proof. So if we need to prove this, all we need to do is show this. But we don't know. Like, so suppose that I didn't know what this thing was. I would have to work out what the right bound is, and I'd have to experiment with different things. But once I know what the right bound is, we can actually prove it pretty quickly. So this is like reading a proof where somebody says, oh, okay, we're gonna prove this. And you're like, well, how did they come up with that? And in this particular case, how you come up with this is just by a bunch of trying some small cases. Okay. Oh, and there's a question. This is theta of n cubed. Remember, y is 2 to the power of the height. So being n cubed is not actually that big if it's 2 to the power of the height. Okay. So here's a base case. y1. Oops, sorry. y1 is equal to 0. Why is y1 equal to 0? Oh, sorry, I shouldn't. That is not correct. y1 is equal to 2 to the power of 0. I forgot that y is 2 to the power of the height. So y1 is equal to 2 to the power of the height for a tree with one node. And that is 2 to the 0, and that is 1. And so we can see that, sorry, again, this should be 1 here. So that's the base case. And the n equals 1. Always make the base case as small as you can. Now, what can we do if we have our base case? How would we go about trying to prove this? It's not difficult. You may be overthinking it. Assuming that we're trying to prove this thing. Yeah, we just assume it's true. And then just go on. So we're going to do that. We're going to do what's called strong induction sometimes. We're just going to assume this is true for all I less than n. Instead of assuming it's true for n minus 1, we're going to assume that it's true for all I less than n. We've seen this a bit before. And then assuming that it's true for everything below n, we can just write those bounds in and say this is less than or equal to plugging the bound in, and then just rearranging. Why do we need to assume that it holds for all I less than n? So the reason is because we'd like to plug it in for not just n minus 1. We'd like to plug it in for all of these. We'd like to plug it in for y1, y2, y3, and so on. So basically what this induction is just, it makes sense. Like, don't think of induction like a rule. Think of induction like making sense. So we know it holds for y1. Assuming it holds for y1, it holds for y1 and y2. Assuming it holds for y1 and y2, it holds for y3. Assuming it holds for y1, y2, and y3, it holds for y4, and so on. Doesn't the standard induction also imply that? This recursion involves all of the lower things, so it's easiest just to put. You could do this. You could do a standard induction, yeah. If you wanted to, probably there would be a way to write it as a standard induction, but this just plugs. You just plug it in for all of these. Does that not make sense? Questions? It's just assuming that this is true for y. We assume that this assume that this is true for y1 all the way up through yn minus 1. Don't we have to verify our assumption? Which assumption? Base case. We go from y1 to y2. We go from y1 and y2 to y3, and so on. Yeah, I think that is probably a cleaner way to write this if you want to do this in one step. I'm just reading what's already written in the chat, but feel free to read what's written in the chat. The inductive hypothesis is that for all I less than or equal to n, this inequality holds. And so we assume it holds up to n, and then we're going to prove it for n minus 1. Or we assume it holds up to n minus 1, and we're going to prove it for n. So we need to prove this inequality holds for the next one. How can we take, how can we ever, sorry, there's a question. Why would we ever use weak induction? Sometimes you just don't need all of the previous assumptions. Often you would just need the last one. I don't like the term strong induction because really both strong and normal induction are just common sense. If you show that it holds for something, then it's going from one step to the next step. They're basically the same thing. There is, we have an inequality here. How can we go from this to what we want to prove? We would like to show that this is less than or equal to a quarter of n plus 3 over 3. How can we do it? Now is where we can break out our hockey sticks. This is the hockey stick identity time. So hockey stick identity is when you have a bunch of different things summed up where you're choosing the same thing. So I plus 3, choose 3, where I is changing from 0 all the way up to n minus 1. So what is this equal to? What is the sum just by itself equal to? Yeah, think about it in terms of Pascal's triangle. If you add up everything, if you add up everything choosing 3, you end up with something choose 4, and it's the thing that you're choosing out of is 1 more than the max of these. So it's n plus 3, choose 4. And then you still have this 1 over n out in front. Now we can rewrite this a little bit. This is just what the definition of n plus 3, choose 4 is. If we put this n in here, we get that. And then we can break out the 1 over 4, and we get this, which is exactly what we needed to prove. Magic. So this is an example of a really clever guess. And I certainly wouldn't have guessed this. But if you guess it right, it becomes really clean. If you guess it wrong, you die in horrible agony. You just have, if you try not to guess it until you have a very good idea of what the bound is. So what was the expected height? This is not done. We're not done. This is a really long proof. Okay, so now we know that the expected value of 2 to the power of the height, which is this yn, is less than or equal to this thing. Okay, we proved that by induction. Great, now we're almost there, we're almost there. But we don't want the expected value of y, we want the expected value of x. Remember, x, we have 2 to the x is equal to y. How do we go from expected value of 2 to the x to just expected value of x? Jensen's inequality to the rescue. So remember, Jensen's inequality says that if you have the sort of function of a thing inside the expectation, you can move it outside if f is convex. Is 2 to the x convex, or is it concave, in which case the inequality would go the other way, or is it neither? I definitely think about these things just imagining the graph. Right? Convex is like it's going up ever faster, basically. Okay, it's convex. Formally, here's a way to prove it. 2 to the x. So remember we worked out the derivative of e to the x, but we never worked out what the derivative of 2 to the x was. So let's just work out what the derivative of 2 to the x is. We have e to the log. So here's a way to you can write 2 as e to the log 2. Sort of stupid, but you can write 2 to the x then as e to the log 2 times x. But that means that the derivative of 2 to the x is just the derivative of e to the log 2 times x, which means, since we know, this is by the chain rule, that the derivative is equal to log 2 times e to the log 2x. Okay, now what do you take the second derivative? We just pull out another log 2, and we get log 2 squared times e to the log 2x, or log 2 squared times 2 to the x. Basically, if you're taking the derivative of a to the x, where a is anything that is not e, then you end up with this in the chat. And this is why. This is a proof of that. I realized we didn't do it before. Anyway, so this thing is greater than 0. What makes something convex is it's greater than 0. The second derivative is greater than 0. Okay. So it's convex, which means that this is greater than or equal to expected value of y, which is equal to, just substituting back in, expected value of 2 to the x, which is greater than or equal to 2 to the expected value of x. That's just applying guesses. And now we're done. We can take the log of both sides now, and we get the log of n cubed, roughly. And the log of n cubed is going to be just big O of log n. And that's because if you take the log of n cubed, you just get 3 times the log of n. So in general, I'm sort of glossing over this a little bit, but it's really simple to show that the log of any polynomial in n is just big O of log n. And now finally we're done. And that shows that, in fact, for this, if you insert randomly into a binary search tree, the expected height that you get is the minimum, up to a constant, the minimum height is just log n. So you're very likely, if you have a randomly inserted binary search tree, to just have it be log n height. Questions? Shouldn't we have to take into account the time complexity of inserting in random order? Oh, so this is just if you're so let's think about what this means. So in many cases, we would expect a binary search tree to have height order of log n. So we'd expect the operations to be like order of log n if the binary search tree came from randomly inserting things. But we don't know that it did. It doesn't necessarily apply to any particular tree. So this is not an average time complexity, really, because we like in real life, your binary search trees might not be random in this way. And also, if you start doing things to your binary search trees, then they really might not stay this way. So what we would really like is a way to make sure that the height is always log n instead of n. And so there's a way to do this. And this is by creating a sort of a better binary search tree, one that self-balances, that automatically makes sure that it's log n. Question. So we were able to obtain a specific expectation by tightening the upper and lower bounds that we found. We never had a lower bound. We just have an upper bound. So big O of log n means that it could be less than log n, but we do have a lower bound because we know that the minimum is also log n. So we know that the expectation is actually theta of log n. But that's the expectation. It doesn't mean that any particular tree has to be log n, and some trees are more than that. So we'd like to make sure we don't end up with a bad tree, basically. Will we talk about binary tree rotations in this class? Yes, we will talk about binary tree rotations in this class, which are mentioned on the problem set. So the particular kind, there are various different ways to create a self-balancing tree. And what a self-balancing tree is just basically one where operations on the tree ensure that it has height O of log n. Yes, red-black trees are really annoying, and I'm not going to go into all of the details I'm certainly not going to go into all the details in like formal proofs, because that would just age all of us. We would not be happy. I want to give you a flavor for it, and I'm not going to test you about red-black trees. There's a reason why there is a problem on the problem set that involves rotations, but it does not require you to know anything about red-black trees. This is just sort of a flavor of how you might do a self-balancing tree, though if you really like self-balancing trees and you want something that's actually a whole lot nicer than red-black trees. So red-black trees are basically awful. They are really, really horrible. But there's a way nicer thing called splay trees, which I really wanted to talk about, but it would just take too long. It requires, yeah, it gets into some complicated math, but it's really beautiful. Red-black trees are just awful. The math is long and awful. Splay trees, the math is long and beautiful. And they're basically magic. Splay trees are magic. Okay. I'm sorry, I'm not going to talk about them. Specifically, a red-black tree is a binary search tree with the following conditions. So it is a binary search tree where every node except the leaves stores a key. The leaves are actually going to store nil. So here you can see all of these are nil. And then why are some of these colored black and some of them, these are colored gray, but I'm going to assume that they're red. Each node except the leaves has two children, has another condition. And each node has a color, either red or black. So these are red, these are black. Pretend that this is red. The root is always black. All of the leaves, these things that contain nil, are black. And if a node is red, both its children are colored black. So here, red, two children colored black. Black, you could have red or black children. So here's a black node with two children colored black, and here's a black node with one child colored black and one child colored red. It doesn't matter. For each node, all the paths from that node to the descendant leaves have the same number of black nodes. So here, for example, if you follow this path, it has 1, 2, 3, 4 black nodes if you count the, sorry, I guess I should have said, yeah, it has 4 black nodes, counting itself. And this one also has 4 black nodes. And this path also has 4 black nodes. Okay. Here is another way to think about it, which is to think of all of these, often this will be implemented where there's a single thing which is called nil, which is the child of everything that is like, it's instead of having all these different leaves, you basically have just one leaf. It's sort of like a data structure way of thinking about it. That this is the only nil and it's the parent of the root and whatever. We're often just going to think of it as just ignoring the nils anyway. So I'm going to skip this for a moment. I don't think we have time for proving that the height of a red-black tree is that the height of a red-black tree is log n. But let's just take this as a given. The height of a red-black tree with n internal nodes is order of log n. Might prove that next time, but I'm not going to get into anything thornier than that, I think. The thing I want to end on is the thing that will enable the definition that will be helpful on the problem set, which has to do with rotations. But let's get into the reason why we're interested in red-black trees. So red-black trees, if you have a binary search tree that has these conditions, it is going to be of height order of log n, which means that operations are nice. Last time we looked at various operations: search, maximum, minimum, successor, predecessor, insert, and delete. Which ones require special attention for a red-black tree? Which ones just work normally? Some of them require special attention, some of them work normally. Which ones that require special attention? We need to modify the rules. So search, maximum, minimum, successor, and predecessor all work normally since they don't change the tree. You're just finding something. You're finding a particular key. You're finding the maximum, the minimum, the successor, or the predecessor. And in those cases, you can just ignore the colors. A red-black tree is just a binary search tree. It just has these weird colors too. Insert and delete are the only things which need to be changed. But all the normal operations are going to run naturally in time O of log n because the height of the tree is O of log n. So there is a way to, and we're not going to go into it here. There's a way to make insert and delete work in a red-black tree. And the way that that works is using these ways of moving around a binary search tree. These are the operations. They're called left rotation and right rotation. And the key point here is that left rotation and right rotation take a binary tree and they give you another binary tree. They do not violate the binary search tree. They do not violate the binary search tree property. What is a left rotation and what is a right rotation? Here, suppose you have nodes X and Y with these subtrees coming off of them. Right rotation means you put X up here and you move Y down to be a child of X instead of X being a child of Y. The three subtrees coming off of them now are connected to different things, but they are still in the same order, left to right. Here is an example. Sorry, this is the left rotation. So left rotation is just the reverse. You go from this side to this side. So what does this look like? Here, let's do a left rotation. This is one subtree. This is one subtree. This is one subtree. So one subtree at 9, one subtree at 14, one subtree at 19. You change X and Y. So now X is under Y, is a child of Y instead of Y being a child of X. And then you have 9 being 9. The 9 subtree, the 14 subtree, and the 19 subtree are all still in the same order. And it's pretty easy to check that this is still a binary search tree because everything in this subtree, this rightmost subtree, was greater than everything else. And it's still perfectly fine in its new place. Everything on the left-hand side was less than everything else that we're moving around. 9 is less than everything else here. 19, 20, and 22 are all greater than everything else here. And the things in the middle, they are all greater than X, but less than Y. And so it's easy to move them from being on the right-hand side of X, meaning they're greater than X, to being on the left-hand side of Y, where again, they're less than Y and greater than X. So these are the things between X and Y. These are the things that are less than X, and these are the things that are greater than Y. And these are just two different ways to write them. You can do a left rotation and a right rotation, and it just moves around these three subtrees, things less than X, things between X and Y, and things greater than Y. In order to do the insert and delete operations in a red-black tree, it involves doing these left and right rotations. I'm not going to get into exactly how that works. But suffice it to say that with a careful arrangement of left and right rotations, you can basically ensure that all of these rules on red-black trees hold, and that gives you a nicely balanced tree that has height O of log n, which is what you want in order for all of your operations to run in only O of log n instead of the possible max for an unbalanced tree, which is O of n. I will stick around to answer any questions. In the meantime, here is a poll about the speed of class. Thank you for listening to all of this first very complicated proof, and then slight introduction to the thorny topic of red-black trees, which I'm not going to go into in more detail.